So for us to understand structure of atoms, we have to kind of take a little detour to talk about energy. Remember, matter and energy are kind of two sides of the same coin. I mean, that's what Einstein's equation E equals mc squared actually tells us or implies, is that energy and mass have a particular equivalency, right? So matter and energy are similar in some ways, even though matter has to do with objects, things we can touch and hold on to and manipulate, and energy is the capacity to do things. It flows through things. It's heat, it's light, it's electricity in terms of current. But it turns out, especially when you get down to the really small level of the atomic and subatomic world, that the distinction between the two gets fuzzy. More on that later in another installment. But to get the background, we need to understand a little bit about energy. And most radiant energy travels in the form of waves, what we call electromagnetic waves. And so there are some characteristics of waves that are important for us to understand that later when we look at electrons and electron behavior will be helpful to have in our toolkit. So every sort of wave, and we could talk about waves on the ocean, movement of water, and we could talk about sound waves, which are areas of compression and expansion of air molecules, but things like light and heat, UV radiation, X-rays, microwaves, radio waves, how your cell phone works and communicates, are all energy waves that travel, and every wave has certain characteristics. It has a certain distance from peak to peak, which we call a wavelength. And based on how long or short a wave is, if we look at how many waves per second hit a fixed point, so here I am sitting in my little recliner chair. Okay, so I can't draw, so don't laugh too hard when you watch this, okay? But we can talk about the frequency with which the waves reach a fixed point. So wavelength, which is shorthanded by scientists with the Greek letter lambda, sort of looks like an upside down Y or a TP with an overhanging roof. Use your imagination however you want to. It's a Greek letter, lambda. And frequency, we use the Greek letter nu, which looks kind of more like a V with a little hook on the back end there. If you feel like it's all Greek to you, it's all Greek to everybody. But that's okay. We can learn a little Greek, and you can get even smarter. So wavelength and frequency, two different aspects of a wave we can talk about that are connected to each other. Okay, so here's the wavelength. Here's me sitting there counting the waves as they go by. Waves, frequency we talk about in waves per second. That does have a unit called a hertz, named after a person who did a lot of work with this. So Hz, you're familiar with hertz numbers if you've ever changed the setting on your radio. That is, if you still use like a radio, like in your car, as opposed to streaming services. FM radio, the numbers are bandwidths assigned to radio stations that are in megahertz, millions of waves per second. If you turn on AM radio, then those numbers, those call numbers, which are the actual wavelengths or frequency bandwidth that a station's been licensed to broadcast on, are in kilohertz, thousands of waves per second. Little aside. Here's the thing about radiant energy waves. They all travel at about the same speed. Now, depending on the medium. In space, they travel at the speed of light, abbreviated as C for Celestina, the celestial light. Okay, and the speed of light is approximately 300,000 meters per second, 3.00 times 10 to the 8th meters per second. And here's the thing, every one of these waves travels at the same speed. So the frequency and the wavelength have a proportionality to each other. The longer the wavelength, the less waves get to you per second, because it's traveling at the same speed as a wave that's shorter, that you'll get more of per second. Okay? So they all travel at the same speed. Here's an analogy. Picture yourself sitting on the side of a highway where you can see multiple lanes of traffic. And in one lane, you have a bunch of little VW bugs, bumper to bumper, all going 65 miles an hour. Hopefully nobody taps on their brakes and we don't have a massive collision. In the other travel lane, you have a bunch of 18-wheeler semis, again, bumper to bumper, traveling at 65 miles an hour. They're both traveling at the same speed. If you and your friend are sitting on the side of the highway and one of you is counting VW bugs and the other one is counting semis, who's going to count more? The person counting the bugs. Why? Because they're shorter. But they're all traveling at the same speed. Okay? Waves all travel through space in a vacuum or near vacuum at about the same speed. Even through air and atmosphere, they're only slowed down or scattered a bit, depending on what's the elemental makeup or the molecules in the air. And then as they pass through things like water and other kinds of media, they do get slowed down. But for our purposes, we're going to always talk about the product of the wavelength and the frequency is about the speed of light. Now this corresponds to energy. So the energy of one of these waves is proportional, that's what that little fish-like symbol means, is proportional to the frequency, which means it also has a connection to the wavelength, right? It turns out that energy, which we measure in joules, it's the metric unit for energy, is the product of, or the value for the energy is the product of a number, 6.626 times 10 to the negative 34th joules per second, times the frequency, which is, again, is waves per second, or sometimes we abbreviate it as s to the minus 1. Anything raised to a negative power puts it on the denominator of a fraction. This number, and that shorthand symbol, is Planck's constant. Max Planck was a German physicist who was studying the absorption and radiation of heat off of matter, off of objects. And what he realized was that the capacity of any substance to absorb and or release heat only occurred in whole number multiples. In other words, it wasn't absolutely continuous. There was no fractional values in terms of the amount of energy that would go in and or come out. And so through his experiments, he ultimately identified this sort of base number, which then could be multiplied up by the quantities of energy. And this is the beginning of this idea of quantum mechanics. I read somewhere recently, this work, Max Planck's work, is what put the quantum in quantum mechanics. Quantum, same Latin root word from which we get quantity, meaning amount. But in this regard, we're talking about a specific amount, only specific amounts. More on that later when we talk about where electrons are and how they're moving. But to take this idea of energy and relate it to what you may already know, there is a whole range of waves out there in the universe, from very short wavelength, high frequency, and therefore high energy waves, cosmic or gamma rays, things that would pass through you and cook you from the inside out, all the way down to radio waves, which again, you could tune into in your car or at home, and in between, you have microwaves and you have the kinds of waves that your cell phone uses. There's heat lamps, the heat that we radiate off that snakes can pick up that our eyes can't. Then, of course, there's the colors of the rainbow. Notice what we can see. Our eyes are radiation detectors. They pick up radiant energy, but only in a very, very tiny piece of this whole big spectrum. And so what we perceive as colors are actually waves of light with slightly longer or shorter wavelengths and therefore higher or lower frequencies. The lowest frequency we can pick up is red. The wavelengths there are about 700 nanometers, okay, or 7 times 10 to the negative 7th meters, so really, really short. The violet light is somewhere on the order of, let's see, we're going from 700 to around 400. nanometers of wavelength. Very narrow band of waves that we tune into and we perceive as light. Above that is ultraviolet light, the stuff that you want to make sure you put sunscreen on so you don't damage your skin, the DNA of your skin, because this can penetrate into the surface layers of your skin. Light bounces off. It doesn't have enough energy to penetrate through you. UV radiation has the ability to penetrate through the first couple of layers of skin and damage some of the living tissue of your skin and accumulate not only sort of sun damage, but DNA damage that can lead to skin cancers. And then from there we have X-rays that, as you know, can pass through almost all of the soft tissue of your body, and only the hard, mineralized, calcified bone sort of absorbs it and blocks it. And then you have gamma radiation, where you need inches upon inches of lead or feet upon feet of concrete to slow that down. Your body would just pass right through, and like I said, kind of cook you from the inside out. So again, from a big picture, just so you have an orientation, the shorter the wavelength, the higher the frequency, therefore the higher the energy. The longer the wavelength, the lower the frequency, therefore the lower the energy. In between, we have the very narrow band that we call visible light, or the visible spectrum. You probably learned it as Roy G. Biv. And you might say, where's the I? And I didn't have an orange and yellow handy, so I just filled them in. But the I is an interesting little story. Indigo, I've seen it put back into some textbooks for a while recently. It had been taken out because it may not be a distinct color between blue and violet. There's some debate maybe about that. The study of light as waves was sort of memorialized or documented with detail by Isaac Newton. And one of the sidebars about Isaac Newton is that he was into a certain amount of numerology. He thought that while he was studying physics and he was a scientist, he also believed that under it all there were certain fundamental numbers that were the basis of the universe. And of course 7 was one of those numbers. 1, 2, 3, 4, 5, 6, 7. If you throw the I in there, you now have 7 colors of the rainbow. But some have debated as to whether that's a distinct color, so maybe it's just Roy G. Or if you read it the other way, from high energy to low energy, VB Gior. Whatever you like. Okay, but there's the visible spectrum. Again, some organisms, like snakes, can see heat at thermal pits, what looks like their nostrils, which are really thermal pits. They can pick things up in the near IR, infrared region. And then you have insects that can see patterns on flowers that we can't perceive because they reflect UV light, and the insects, bees for example, can see things in the near UV range that we can't see, that are beyond our ability to pick up. So, just a little bit of interesting aside stuff here. The take-home, waves. Energy travels in waves. Every wave has a wavelength, which then corresponds to its frequency, which is also related to the amount of energy the wave has.